Hello students, today we'll be going over the Diels-Alder Cycloaddition reaction. So this reaction was named after Otto Diels and his student Kurt Alder, and the pair went on to win the Nobel Prize for Chemistry in 1950. So the basis of the Diels-Alder reaction is a double alkene, a diene, reacting with another alkene group, forming a final six-membered ring with a double bonded group in the product. So the diene is acting as the nucleophile in which these electrons here, this pair of electrons here, will form the bond between the nucleophilic carbon and the electrophile, and pushing off this double bond here, a pair of electrons forming the carbon bond here and here, and finally pushing this final double bond onto here, making our final alkene product in the cycloalkene, or the cyclohexene. But while this is a concerted reaction, we have a transition state, a sort of semi-aromatic system. So on to the electronic nature of the substituents. So the diene is acting as the nucleophile. So the more electron donating, or the greater the electron density here in the center of the molecule with the nucleophilic carbon, the more reactive it will be. So electron donating substituents will increase the electron density in the center of the molecule, increasing the rate of reaction. And some examples of this, or of some electron donating substituents, would be alkyl groups, or methoxy, or carboxylic acid. As well, on the dienophile is acting as the electrophile. So the more electropositive this center of the molecule is, the greater the reactivity. So electron withdrawing groups will lead to a quicker, more effective reaction. So just some examples of that are a halogen, or different halogens, or aldehydes, cyano groups, nitro groups, and so on. So what also determines the rate is the structure of the reactants. So for the diene, it needs to be in cis conformation in order to react. So here we have a diene locked in the cis position. So this will have a much higher reaction rate than other similar dienes. What also determines the rate is the steric hindrance. So here we have two similar groups of the dienes. So here we have two methyl groups pointing outward and pointing inward. So this is acting as the nucleophile. So with these methyl groups pointing inward, with their hydrogens being above and below the plane of the molecule, this will highly interfere with its nucleophilic attack on the electrophile. So something special about the Diels-Alder reaction, or I wouldn't say something special, but something that happens with the Diels-Alder reaction is that when this reaction takes place, the two reactants are a bit above and below each other instead of acting head-on. So if you can imagine the methyl group sticking out here, or their hydrogens being above and below the plane of this molecule, they would be interfering with the electrophile down here below and a little bit shifted out. So you can see how that would interfere and slow down the process. And here we have the diene just locked in the transposition. So this will not be able to react, and the reaction rate will be essentially zero. All right, so here we have our more of the stereochemistry. So the substituents will also not only determine the reaction rate just based on their structure or the induction of the electronic nature of the substituents, they will also determine the final stereochemistry of the product. So here we have the dienophile in cis position with different substituents. So with it being attacked in the cis position, we're going to form a final product in which both of the substituents are facing into the same face of the molecule in the same plane. So they're both, in this case, sticking outward. They're pointing the same direction. So we call this, with this plane of symmetry here between the two similar stereocenters, a meso product. Here, with the dienophile being attacked in the trans position, we're going to end up with a racemic mixture, so a pair of enantiomers in which these are not the exact same molecule, with one sticking out, one sticking down below. And have you flip this molecule from this position to this position, it's still going to look exactly like this. And you can never make these two, you can never make this overlap with that just by shifting it around. So these are two different molecules, a pair of enantiomers. So the substituents will determine the final stereochemistry of the product. Here we have a special bicyclic formation. So here you notice this dienophile is already in a cyclic structure. The diene is. So when it attacks the dienophile, this carbon attached to these two carbons will have to go somewhere. So it will be sticking above or below the plane of the molecule, depending on how the molecule is oriented. So here we see the final product of the final double bond will be, as you can see here, the final double bond will be between where the other two were. So this is that final formation, with this final carbon, this point here, being above the plane of the molecule, and the substituent here being in one of two different conformations. So here we have it sticking out and away from the rest of the molecule, away from the double bond. So we're calling this exo, where here it is sticking out below the rest of the structure, and with a little bit of steric hindrance with any of these groups sticking out here below, and we're calling this endo. So depending on the temperature of this reaction, you could end up with more of one than the other. So here we have just two special examples of the Diels-Alder reaction. Here we're using a triple bonded molecule as the dienophile. So the final product will end up with another double bond instead of just the one that formed originally. And here, with this special molecule, we're able to have this one be the dienophile for two dienes, for two molecules, resulting in two six-membered structures on either side of this final molecule. So we're able to react twice as much with it. And so, just going over the final reaction that we'll be doing, we have a 3-sulfolene reacting, or we'll be using that after we heat it up as our diene, forming this sulfur dioxide and this 1,3-butadiene molecule. We'll be reacting the diene with malic anhydride acting as our dienophile, forming two final products, either an exo or endo enantiomers. So I think this is a pretty cool and pretty important experiment. I really like this type of reaction. It was really interesting whenever I did it back in Organic 2. So I hope you guys have fun with this final experiment. I'll see you then.